Have a guess. It was 78 cost savings. Because, I mean, you need less pins to the outside, so they want to have, these things need to be sold to the general public, so they want to reduce the cost of things. 128 bytes of memory. That's basically spelling your name, forwards and backwards. So it's very little, depends on your name, maybe a Mexican name just forward, because they have very long names in Mexico. You do have sprite hardware, and this is interesting because I think the Atari was one of the first machines that had sprite hardware. If you want to call it such, because it was nothing like the sprite hardware you have in modern machine, where you just give the coordinates of a sprite and it will render it. No, it was more complex than that and more primitive than that. You had 8-pixel player sprites, 1-pixel missile sprites, each 2, and then a ball sprite, also 1 pixel. The width was limited, but the height was basically unlimited, so you can have the whole screen. So that was one of the advantages by the design. And you have a low-resolution playfield graphics. I think you had 6 pixels per block, so you can do some backgrounds. It had nice colors, 128, looking much nicer than the C64, which had a really horrible color palette. But, I mean, you can choose from a lot of colors. Only problem is you can only use one of them. So that was a little bit of a constraint. So these were the color palettes. And in this time, we had different standards for TV signaling. So we had NTSC, I think, which was popular. Was it in Germany or in the US? I think in one of them. We had PAL and SECAM as well. And the Atari could support all of these in some way, but the colors slightly changed because of the varying standards. But you can see there's a lot of nice colors here you can use in your games. And so from that point of view, it was quite sophisticated, I would say. So this is a board. It looks very simple. So there's not a lot of here. I mean, you have, this is probably a power regulator. This looks like some sort of RF encoder for the higher frequencies. You need to send this to the TV, so they need to be modulated and coded. And then you have only 3 chips. The heart is the smallest one, the CPU. And if you remember, you went to Jose's talk. He gave a talk where he showed that CPUs are getting smaller and smaller, so they're not anymore the biggest part of a system. It used to be, but now the biggest part is probably the graphics processing hardware. And this was the same here. So you had 2 chips, the TIA and the Riot. And I'll say a bit more what these chips do, but this is a very typical design of these systems, that you have like some special chips which deal with gaming issues like graphics and sound, and then you have a CPU that feeds these chips. So the Riot chip, if you go back here, the top one, it includes the RAM. It had timers, which is sometimes useful, and it had bidirectional input-output ports, so that you can have your controllers. Yeah?
Does that stand for something?
Pardon?
Riot? Does that stand for, is that an acronym?
I think I/O stands for input-output. RAM, R probably stands for RAM, but I'm just guessing. So, yeah, it's not about it. It's an acronym, of course. Yeah. Yes. Thank you. Nice. Nice. So the TIA stands for something else. But this is basically the video generation chip. And yes, television interface adapter. Thank you. Yes, that's true. That's true. Now I have to break you something. This chip didn't have a frame buffer. What does it mean? I mean, Josue now said, of course, because he's your device programming guy. But for everyone else, that means you don't have a graphics memory. There is no memory in the system that stores your graphics in terms of pixels. So all you have is this 128 bytes. And you're not going to use this for graphics. You're going to use it for your game and for your stack frame and whatever. So how did it generate graphics? it was a bit weird. So the TIA and the CPU do it together. The TIA is actually the thing that generates the graphics, but it needs constant input from the CPU. So in order to write a game, you have to constantly tell the TIA at each scan line what you want to display, what's the background color, what's the play field, where the sprites are, and so on. Now, this sounds like a bit tedious, and it actually is a bit tedious, so you see that a lot in code when you look at it. But the real issue was timing, because imagine your beam is not going to stop for you to display the graphics. So you have a certain speed at which the beam, and this was before we had like modern displays. These were all CRT displays. So they had a very specific way how they display graphics. There's a raster beam that just scans all your screen. It does it at a certain speed and frequency, and you just need to feed it the data in time. So the CPU would feed the TIA with the data as it's needed. And that was always a bit of a problem, because you only have a certain amount of time to do that. And I just want to be a bit cheeky, and I will show you a screenshot, if I can find it here. Just give me 1 second. Let's maybe put this one. If I don't find it, it's not a big problem. Yeah, I can't find the screenshot now. There's a course. Yeah, just forget about that. I'll just continue and I explain this when I go to the next slide. Cool. Wrong talk. This was about something else. Oh my God. Let me see if I can have my talk back now. This wasn't the right one, but let me see. Wait. So, yeah, I'm back. Cool. So, just to appreciate how this really worked, this is a game which was quite popular at the time. And what you can see is you have graphics, objects that kind of move. You have this thing that moves, you have another character which is multi-colored, and so on. So when you look at this from like 2000 perspective, Generation Z perspective, it's not really impressive, right? But if you look at this from the actual efforts of the developers, it's really impressive, actually. The first thing you notice is that this thing is multicolored. So this can't just be a single sprite. How did they do that? They change the color each time you go to the next raster line. This is probably some sort of player sprite they used here. Then this thing is also more than 8 pixels, it seems. I'm not quite sure. I haven't counted it. You have, of course, the rolling objects here. There's 2 of them, which in fact already takes up 2 of your sprites. So there was a trick basically to duplicate sprites as well. You have this logo on the bottom. Even just making that logo is hard. It's not easy. I mean, once you start programming this thing, you need to really see how do you place your sprites. This is probably just sprites basically placed next to each other, because you wouldn't get this resolution with the playfield background. So here you see the background, because that's a lower resolution. But this one looks a bit more higher resolution. And they do a combination of the player sprites, the ball sprites, and so on, and that's how they display this. This takes a lot of code actually to do, just to, as I said, there was no frame buffer or anything. If you go to the next game, this is even cooler, because you see there's a lot of colors here. But you only see the colors changing vertically. So for instance, you have here a lot of vertically changing colors, but horizontally you don't have many changes. Why is that the case? Yeah, I mean, couldn't you? The thing is, it's very difficult to do, and this has to do with the clock speed of the CPU. So the CPU is comparably slow comparing to the pixel clock. I think there's a factor of 3 times slower, either 3 or 9. I'm not saying, hopefully not saying something wrong, but the CPU, I think a write of the CPU takes 3 cycles. 1 cycle is 3 pixels. So you cannot change quick enough here the colors. So you need to initialize them at the start of the scan line. And this kind of tells you a bit more how you're doing these things. When do you do computation? Well, your beam is going to traverse the screen. And there's 2 places where you can do your own computation. When the beam reaches the end, it needs to go back to the start. And you have 76 CPU cycles of doing that, precisely. And everything that you're going to display here needs to be in 76 cycles. I mean, you can cheat a little bit by saying, well, this thing can be set a little bit later, because if the beam is somewhere here, I can send the data for this thing. It's possible. So there are these kind of tricks where you need to think in terms of timing. The other thing you have is the vertical, this is, by the way, called the horizontal blank. The vertical blank is when you're reaching the end of the screen, and then you're going to go back to the start. And this is a bit more generous in terms of timing. But all your game logic either fits into the into the vertical blank or the horizontal blank. This is all the time you have to do your game logic. And that was a little bit tricky to get your head around in some ways, because most of the time the CPU is actually creating the screen for you. Is that? No. I thought it was my cap. Anyway, so here's another one which I find impressive. And the reason this is impressive is because when you play this game, you see there's 6 objects which kind of seem to move independently. And doing this is extremely difficult. First of all, because these objects are also quite wide. And then, how do you make sure that that you can have two sprites on the same line? The issue was always that you only have 2 player sprites on one line. But I mean, if you have 3 or 4, it's very difficult. And on top of this, there's also shooting stuff. So when I see this and I look at the limitations of the system, it makes me really kind of in awe how they managed to achieve that. So I'm running a bit out of time with the talk. So I just want to quickly tell you what tools you can use to write these games. So the main tool you need is an assembler, which translates your machine code, which is, by the way, almost like a cross-compiler. So it takes your assembly and translates it for the CPU. You can't run it on your machine natively, but you can use an emulator to do that. So there's this Stellar emulator, which exists for most systems, and it's quite easy to install and use. So it runs on a Mac, runs on Linux and Windows as well. When you do this, you need to understand your CPU. This gives you a bit of an idea how limited the CPU is. The CPU has only 3 registers, A, X, and Y. All your computations need to be done using these 3 registers. These are also called index registers because you can use them to do indexing relative to some memory address. They can be used as counters, which is often the case. You have a status register, which is important when you do branches. So when you compare 2 values, the status registers will be initialized sometimes to set the 0 or the carry flag. So you can test if a value is equal to 0. You can test if a value caused an overflow or carry. So this is very important for your control flow of the program. You have a program counter and a stack pointer. But the stack pointer is kind of not something that I would use that much when I write these games, because the operations on the stack pointer are very time consuming. So sometimes they're really useful to optimize, I think, but you need to be careful writing naively code. So sometimes a direct branch can be quicker than a stack pointer. there's the competitor of this processor was the Z80. So you find the 8-bit machines, either they had the 6502 or the Z80. And the Z80 had more registers. But the 6502 made up with the 0 page. And the 0 page is basically the start of your memory. And you can very quickly write to the first 256 bytes of memory. So that was a way to get around these limitations that you only have few registers. So you can shift stuff in and out of the 0 page, and that is a bit faster. So you also had interrupts, but I think the Atari didn't really make much use of these. This is all your instructions. So that's all you need to understand what these instructions do. I mean, I don't want to go into too much detail, but you have load instructions where you can load registers with constants or from memory. So these have usually different addressing modes. You have arithmetic instructions, you can add stuff, you can shift, you can do other things as well. You can have logical operations like AND and OR, you can rotate. These are all stack. What?
Jump.
Jump, yes, you have a jump operation, so go to is not harmful. Well, at least not here. It's the only way to do it, basically. And you have various kinds of branches. So the B instructions are conditional. So they're looking at your flex, and the branch might be executed or not. So you can find quite a lot of references of this stuff, and it's quite easy to find out what these instructions do. But the important thing is, you need to understand them. And that means not just to know what they do functionally, but also to know the size. So instructions, how big are they? How much memory they take? How long does it take to execute them? Because that really affects your budget of time that you have to write the games. Changes to flex. I mean, do they set your flex? Or the stack pointer? Sometimes what makes it really difficult is if instructions are on page boundaries. And here a page is only 256 bytes. Sometimes they take more time. So they are kind of having an additional cycle, and you want to avoid that because it can disrupt your timing. And sometimes it's even important to know precisely how they work on the bus. So an instruction that takes 8 cycles will not immediately write data to the bus or read data from the bus. So this is very important to see how the chips interact. So you're getting one way lower, and you need this if you want to have rock solid, let's say, stable display and timing. Not always, but I mean, that's the consequence. Cool, graphics kernel to do. As you can see, I run a little bit out of time today preparing those slides. But I will show you instead maybe a demo just to see how this actually looks in practice. I have a couple of things open here. I can maybe, let's see. Let's just use this one.
Does the Atari allow you to expand the RAM with the cassettes?
Yes, the modern cartridges do that. The original one didn't, but the modern ones. So this is a very simple demo, which just has a moving background and a logo that bounces up and down. I wanted to show you some sprites as well, but I didn't have enough time to write this. And as you can imagine, coding for this thing is not so easy. So you might, but no, please. No, that's, I feel embarrassed now because that's a very simple thing and it doesn't deserve the name game. But I want to show you a little bit of the code. So let me see if I can make this a bit bigger. The settings, font, let's put it maybe to 24. Make this a bit bigger. So this is the simplest example that you can write, and this just produces a gradient in the background that doesn't move. So if I execute this, it will just produce a gradient. So this is how you write your code. And let's talk through it. So you need, at the beginning, this, I'm not sure this is just a label that you can jump to, so it just addresses. At the beginning, you need to tell the video hardware that you do a vertical blank. Now, if you know something about video signals, they have a very precise kind of structures. So you need to tell them when the beam retracts. So here I'm basically telling the beam to retract. And here I'm sending the sync signal for doing that. So the blank is basically remove any color output, then you're sending the sync signal. Now, this is a very interesting one, where you're writing to a register, and this is called a strobe register because it stops the CPU. So it's a very weird, you're writing data, but your CPU is going to wait. It's going to go, you can always make a CPU wait. Most CPUs have some way where you can insert wait states, for instance, if memory is slow or things like that. So basically, I'm waiting for 3 lines, 3 scan lines, and then I'm setting the vsync to 1. So now I've finished the vsync. I've given 3 scan lines of vsync signal. And now I'm inside what's called the vertical blank. It's an area which you don't see, but which you can use for your game. So this is a very badly written code, because I could have done all of this in a loop and would have saved a lot of memory space. But just to tell you that you can start with something like that. And I'm waiting for 37 scan lines, basically, to pass. So what we're doing here is not just programming, we're generating a signal for the TV. And I mean, this is the level that you program these things. No? You're generating basically the signal for the TV. Yeah, we are just overrunning, but I will show you this code, and if there's interest, I might do a more elaborate presentation on the demo and explain how that works. So all these vsync signals, and now you're in the first line of your screen. So this repeat is a macro. Is just say, take this piece of code and repeat it. So I'm not even using a loop. I'm just using a macro that expands this piece of code 192 times, because there's 192 scan lines. So I have a register X, which I set to 0. Then I increment X, and I write this to a special register that changes the background color. And this is how all of this works. You have a lot of special registers that change your sprites, your background color, and so on. And then I'm just waiting. I'm writing to vsync, which makes the CPU wait. So there's some hardware, when I do that, that recognizes me. I'm writing to this and stops the CPU until the next scan line. And this generates basically the gradient, the background. And once I reach the end of screen, I'm again writing some data. This is just writing a value giving in binary. So the assembler allows you to write a constant. So I'm writing this constant into my accumulator. I'm waiting for my vblank. And now I'm executing 30 scan lines of waits again. So I'm now in what's called the overscan area. So the picture at the beginning has a vertical blank, and then it has an overscan area. And this again is usually where you put your game logic. And I just jump again to the start. So this is the simplest, one of the simplest programs, but it gives you an impression of the level that you're actually working. And if I execute this code, let me just see if I can run it. I can maybe just change the make file. And I think this is what it does. So it's extremely simple what it does, but it's not trivial. And you can shorten this code. The code is written really to give you as a first step. I can quickly show you the code for the second program. So this is the code for the second. And one thing you notice in this code is that I'm writing a lot of comments. And the reason I'm doing this is because it is very hard to keep track of assembly code. And without a good discipline of commenting, you're going to lose very quickly track of things here. But in essence, I'm doing the same. There's some differences here. For instance, that at the beginning, I'm initializing some registers. And these are all in the 0 page that I explained to you before. So this is the first part of your memory. And then, again, you're creating your vsync signals. You have your overscan vertical. But instead of using the repeat, I'm actually using a loop here. So I'm setting a register X. Then I'm waiting. And then I'm decrementing X. And then I'm jumping back if I'm not yet 0. So this is how you do a loop in assembly code. So you're choosing a register, you're setting it to a value, you're incrementing or decrementing it, and then you're checking, you do a conditional jump. So B and E means branch if not 0. And this is how the code basically goes. I mean, there's a few, here I'm initializing the background color, and the actual loop for the scan line starts somewhere here. So I don't want to go into all the details, but one thing you can see is this comment about cycles. So I'm actually counting cycles. Why? Because I need to know that I'm not overrunning the scan line. And you need to be careful that whatever you do at the start of a line is not going to overrun the line. Otherwise, you're going to end up with some tearing on the screen, or other things. There are some subroutines here that generate this kind of background, the background image. And they need to do that at the right kind of place. So you're basically doing a comparison here where you decide if you start painting the logo, the ESG. And you do that based on the scan line. So your white register gives you the scan line, and this ESG start is basically where the logo starts. So this is a 0-page variable. You're comparing the two, and if they are equal, you're painting the logo. Otherwise, you're just continuing and going to the exit here. So it's very convoluted, nothing like structured programming. And you need to find your own way to make this comprehensible in a way. One more interesting thing maybe to say is if I go down here, so I'm counting, this is very meticulous. You have to count all the cycles. But when you see the logo bounces, it's a gravity bounce. So let me just put this back. So what is the problem implementing this? Imagine your boss or someone tells you have to implement this. What's your first impulse? Bearing in mind this very limited CPU language. I mean, of course, you can make it look like it bounces, but how would you make something look that obeys the laws of gravity? You need to solve a differential equation for the acceleration and the speed. Now, when you're solving that differential equation to calculate when you should paint the logo, and you parameterize it by time, you're ending up with a quadratic formula. And because it's a quadratic formula, you cannot easily implement it, because there's no square root operation or multiplication in the CPU. So you need a bit of trickery. The first trick is,
Static table?
You could use a static table. That's what a lot of people do who've writing speed code and who are doing impressive stuff. So that's a possibility, but assume I don't want to waste a kilobyte for a table or something like this. So you can solve this differential equation iteratively. So instead of just having the position of the logo, I'm also keeping its velocity. And then the operation just becomes a difference. So you can just calculate, you take the acceleration, you add it to the velocity, then you take the velocity and you add it to the location. And by doing it in that way, you can do it with just addition. You don't need multiplication. But you still have a problem with floating point numbers. And surprise, there's no floating point engine in this thing. So what you can do is you can use bit shifts. So you can use a fixed point floating fixed point, not a floating, but a fixed point encoding. And just to quickly show you, I don't want to discuss all the code of that, but if you look at this again, the actual code that does that is this code here. So this implements the gravity bounce. And again, everything is just written in assembly code, and it is almost impossible to understand what goes on here without really knowing the approach. So the acceleration in this case, I think the way it's implemented is a fixed point number. And the sort of bouncing effect that you reduce the acceleration, I think takes place, I don't even know myself now. Yeah, I would need to look at this code myself. I'm embarrassed about it, but then again, I haven't looked at this for two months. But you need these clever techniques. And you also see comments here. What happens if something gets negative? How do you deal? I mean, you have 8 bits, basically. That's all you have to compute. Most registers are 8 bits, so everything needs to be in 8 bits. And you need to do sometimes some simplifications to make this actually possible. And even if it's not really bouncing, if it just looks like it's bouncing, that's still, and this is something that games programmers do, I think, quite a lot, to find these shortcuts to accelerate things. But I'm going to make the code available despite being embarrassed about it. And the last thing here is that I'm using a timer. So instead of having the synchronization in every scan line, I'm using a timer here to make sure that I don't waste too much code doing this, and when the timer expires, I know I have the scan line expired. And you can use Stellar to debug that all of this works, but it's not obvious from the code. So I feel bad now because I might have put you off writing code like that. But at the same time, maybe you appreciate, there's a very nice book called Racing the Beam, if you want to have a look at this. Maybe at the same time you appreciate the efforts of these people who write those games. I mean, E.T. was mentioned to be the crash. I mean, E.T. caused, it was the nail in the coffin to cause a games crash for the Atari. But this game was written in 6 weeks, and it wasn't that bad. I mean, so it's a different kind of skill, but you get used to it. And at some point, if you write a lot of comments and you kind of try to be very clear and clean in your code, you can actually write stuff for this. But it's not a walk in the park. But it's gratifying, because if you manage to do something and it actually works and it's stable, I mean, even if it's just one sprite moving on the screen. Sprites are another issue. I mean, they are even more difficult because you need to write to a register at exactly the right time to place them. So they're like counters. And you need to reset the counter at the right time, and then the counter will trigger the sprite. So basically, you're writing a code that waits for the right position on the screen, then you write to it, and then the sprite appears at that position. I mean, how more difficult can it be? I mean, it's not like in a Mario, or when you can say, or more modern systems where you can say, I want the sprite to be here and there. So since we are running really late, and Cynthia wants to go home, thanks very much, and I'm really happy that we had so many people coming. The community is really you, so I will try my best to nag people about giving talks and stuff like this, and we will maybe have more talks about this, about other things, whichever interests you. But yeah, thanks very much for coming today.
Esta es una comunidad que mes a mes está aquí en el garage, generalmente es a fin de mes, así que pues bienvenidos, se pueden sumar ya sea al WhatsApp, hay también una página de meetup. You have a meetup page?
Yeah, so we have the meetup page. If you're not a member of it, you can join it. We have a WhatsApp group, so let me just share with you the WhatsApp group. Maybe I can put the link somewhere if you want to take a picture of it.
Y de cualquier manera también nosotros ponemos en la página del garage, tenemos una parte de eventos y ahí ponemos todos los eventos que tenemos al mes. También pueden acceder a la información desde ahí. Y pues nada más, pues muchas gracias. Frank, you need to say something now?
Yes, muchas, sorry. Muchas gracias. And just before you go, I just put it here. This is a link for the meetup page. And if you want to take, I'm not sure, maybe it's too small. If you want to take a photo of this and then join the chat group, you're very welcome. I might send actually a message around. Let me see if I can make this a bit bigger. Sorry about that.
The link is in the meetup page?
Yeah, so let me see. Gedit settings. Let's just make this maybe 40. And let me make this bigger. So if you want to take a photo, maybe it's the best thing to do. Yeah.
Muchas gracias.
Gracias. And we might go for a drink if you like to join us for beer. So there's definitely going to be a few of us, David, Daniel, and Claudio, and maybe a few more. Feel free to yeah. Cool. Feel free to join us.
Something that comes to my mind
Yes.
when you said that there is different memories, how they calculate the hitbox for the game. Yeah, you know, in Space Invaders or something like that.
The collation.
I was going to say, I have the code to Space Invaders, and I've been going